Okay, now to a second type of triangle, and this one is equally as nice, maybe nicer than the 30, 60, 90 triangle, and that's the 45, 45, 90 triangle. I've snuck this in on you a few times already. I gave you some squares to work with and asked you to work with the Pythagorean theorem with some squares. So I want you to imagine that if I had put a square out here and drawn in the diagonal like all those TV problems, we might have this little piece going on. And in a square here, we know that that diagonal is going to cut those corner angles in half. So we have a 45, 45, 90 triangle. And I think everybody agrees that in squares, or in 45, 45, 90 triangles, those legs have to be congruent. And if I did a Pythagorean theorem, 1 squared plus 1 squared equals c squared, I'd get 2 equals c squared, or the square root of 2 equals c. And there you have your 45, 45, 90 triangle relationship. The two legs have to be equal, and the hypotenuse is always the square root of 2 times whatever your leg is. So if you go back and look at maybe a couple of problems that we've done, I think back to one of those quizzes where we had a TV, and maybe we had a 36-inch screen on our TV, and we were trying to figure out maybe how much the diagonal was or something like that. Here, because these legs have to be congruent, it's 45, 45, 90 triangle, the relationship says these have to be congruent, and your hypotenuse always has to be whatever that leg is times the square root of 2. There's no way around it. We could do our a squared plus b squared equals c squared, but you know, you do 8, 9, 10, 20, 30, 40 of these, and it gets kind of boring. So let's not do that. Let's look at it and say, we know what this is going to be, and come right down to it. For all you baseball players, anybody that plays baseball, the game of baseball is a diamond or a square, and if you talk about the distance from first base to third base or second base to home plate and the other bases, we always have a right angle in the corner, and then these distances from one base to the other base have to be equal. I mean, they can't be different, or it wouldn't be a baseball field or a softball field. So if we go to baseball, if we're going to go play baseball, the bases are further apart. They're 90 feet apart in baseball. We go out there to the Valley Field and we measure the distance from first base to second base or second base to third base. We're going to get 90 feet. Now, if I want to know how far it is to throw it all the way across the diamond from first base to third base, I don't want to go get a tape measure out there. I want to say, well, 45, 45, 90 triangle. If these two legs are equal, then the hypotenuse has to be that leg length times the square root of 2. And you're welcome to do a Pythagorean theorem and prove it, but why? Why prove what we've already proven to be true, which is if the legs in a right triangle are congruent and it's a 45, 45, 90 triangle, the hypotenuse always has to be the square root of 2 times as much as the leg. So it's really nice when they give us a leg that's an integer, because then the hypotenuse is just the square root times that. Where it gets more interesting is when, of course, the numbers aren't as nice as what they could be. Congruent legs, which means it's a 45, 45, 90 triangle, and maybe they try and trick us and they give us that the hypotenuse is, we'll work backwards. We'll go with crazy 11 square roots of 2. And I started to think that maybe that was going to be a trick problem, but since we know the hypotenuse is always the square root of 2 times the leg, it looks like we have the square root of 2 times something, so that leg and the other leg both have to be 11. I can just look at it and say, no problem, it's 11. All right, so there has to be something more challenging. I think I can make a more challenging question. Leg and leg are congruent, 45 degrees, 45 degrees. I think I'll put some crazy number like 3 square roots of 5. I mean, completely wrong. Not even anything I was considering at all. This looks really, really strange. But I want to go back to what I did with the 30, 60, 90 triangle. We have a ratio. We know that a leg compared to the hypotenuse in a 45, 45, 90 triangle is always the leg is 1 and the hypotenuse is the square root of 2 times as much. So if I put my ratio down that a leg compared to the hypotenuse is always 1 over the square root of 2, the leg we don't know. We have no idea what that leg is. That's our job to find it out. And the hypotenuse is 3 times the square root of 5. We see a proportion again that we get to solve by cross multiplying. So if I cross multiply, the square root of 2 times x equals 3 times the square root of 5. And now we have to solve this equation just like every algebra equation, so we divide by that coefficient. So we can divide by that. And technically, we have a pretty good answer, 3 times the square root of 5, all divided by the square root of 2, but it's not rationalized. And in upper level math, they always expect you to rationalize denominators. They don't like denominators that are radical numbers. So just like we did last time, if we want to rationalize, we multiply both the numerator and the denominator by the square root of the denominator. And now we just have to remember how to multiply radical expressions. The square root of 5 times the square root of 2 becomes the square root of 10. And the square root of 2 times the square root of 2 is kind of like doing a little factor tree. That becomes a 2. And now we have our 45, 45, 90 triangle. We can hopefully figure out any missing edges, and it can make our work for finding these legs in a 45, 45, 90 triangle a lot more effective.